So here's our speculation from looking at the graph. The derivative of sine of x is equal to cosine of x. So cosine of x tells us the rate of change of a sine of x at any point. I mean, that's actually a pretty remarkable and interesting thing. I find this very interesting thing in terms of seasonal changes. So in particular, how the length of the day changes throughout the year. That's actually tied up in here. So if we think of sine of x here as representing the variation of the length of day with the seasons, and the cosine of x, since it's the derivative of sine of x, it's representing the rate of change of the length of day at each season. So for example, if this graph begins with the longest day, which is the summer solstice, and then here's our intermediate day, the autumnal equinox. Here's the autumnal equinox. That's where we're at right now, okay, is the autumnal equinox. So what's interesting is the autumnal equinox is sort of intermediary in terms of the length of the day. But what you can really notice this if you think about it. What the cosine is showing is that at that vernal equinox, where the length of day is the average between the longest and the shortest day. So the length of the day doesn't really become negative. So you want to think of the zero as being like down here somewhere, okay? So the rate of change at the autumnal equinox is the highest, all right? So when we get to these intermediate autumnal equinox days, and it seems like the seasons are changing so rapidly, that's because they are, and this graph shows why. Because if the length of the day is changing sinusoidally, then the maximum rate of change occurs at the autumnal equinox. Then here we have the winter solstice down here, right? So this is the winter solstice. This is our shortest day. I mean, think of the negative being below the average length. So the zero is like the average length of a day. And by the way, we're also throwing out in this analysis daylight savings time, which is stupid and destroys our like circadian rhythms. Anyway, here at the vernal equinox, the rate of change becomes, this is the winter solstice, the rate of change of the length of the day becomes zero. So at that winter solstice, the length of the day is not only shortest, but it's changing the least rapidly. So you have those long nights, and they also are just staying long. That's what it feels like, because that's what's actually happening, because the rate of change is zero. In fact, that word solstice is from the Latin solstice, and sol, of course, means sun, and stice is like the word stasis, and it means not moving. So even back in very ancient early astronomy, people described the solstices as the time when the sun is not moving, in the sense that the rate of change has become zero. So it's like the sun is not moving. It's not changing its length of the day. And then we come around to the vernal equinox, so the spring equinox, right? Now, the rate of change is I think I actually switched the equinoxes somehow. Because the rate of change is far from average, but this time it's negative. So that should indicate that the days are getting shorter. Yeah, now I'm going to be staying up nights thinking about this. So when the days are longest, you are at summer solstice. Then you have autumnal equinox. Seems like the rate of change should be negative because the days are getting shorter. Well, I'll think about that more later. I don't get bogged down in it right now. So, right, at the solstices, I know what it is. This graph, the sine graph, is the length of the day, and the cosine graph is the rate of change. So this graph actually starts at vernal equinox. Rate of change is positive, means the length of the day is increasing at a maximum rate. That's why the days seem to get longer so much more rapidly at the vernal equinox. Then summer solstice, the days are longest, but the rate of change is zero. They're not changing in length at all. Then we get to Autumnal equinox, this is where we're at here. Length of the day is 0, means average in this case. The rate of change is its maximum negative rate. So that means the days are getting shorter. That's why the rate of change is negative at its maximum rate. So that's why at around September 20th, you'll notice that length of day changing at the most rapid rate. And that actually happens. And then, see now, it should get me lost on there. Then we're going to go, let's see, this is our length of, this is our day. Vernal equinox, summer solstice, autumnal equinox, winter solstice. The length of the day is shortest. See, we're at the minimum for length of day. And the rate of change is 0. So the day is short and it's staying short. And then we get to do it all over again. We get to vernal equinox. The day is medium length and its rate of change is fastest. So think about that when you're looking at the seasons. Calculus is everywhere. It is in everything. Okay, the next thing we're going to do, what we've just observed is the derivative of sine is cosine. Here's what it means and what we talked about. And the next thing we're going to do is prove why this has to be true from our limit definition, which is that the derivative of sine of x. See, anytime we want to get what the derivative of something means, we have to go back to the limit as h approaches 0 of f of x plus h minus f of x over h. And you can see what the problem is here. Nothing is going to just cancel out. So that's what makes this a more difficult problem, which we'll look at the next video.